today.
Okay.
View login location.
Yeah, they ask you to check your email.
Yes. My God. How come today this is so complicated?
Because they check you are logging in the new location. Maybe the reason is because you changed your setup today.
Okay. Verify Discord location. Okay. Okay. Log in. Log in. Okay. Huh. Weird. Okay, let's try this again. How come this should be working now? Okay. How come this camera now is not working? If I don't use this, nobody can see the slide. That's the problem. Okay, let me try and disconnect. Ah, wait. Do I need to install? Because last week that all worked easily enough. So what did we change? That's all the same. And that camera is on. And this one I don't need. Discord. Is Discord running now?
I'm not sure. No.
So yeah, now this is not going to work because it doesn't have the thing. How can I get this one? Okay, so in that case, the only thing I can do is set up streaming. But it's very strange because last week this all worked fine.
Are you using the same computer?
Yeah, it's this one here. But of course, maybe if they rebooted it, it's going to be completely reset. So let me try this OBS Studio Virtual Cam. Running. This means running. The first one.
Yeah, exactly.
I think that's the problem. I didn't set up the.
Right.
So who felt the earthquake yesterday?
Yeah, me.
That was the scariest one I have
Yeah,
experienced
me too.
in Taiwan. That was pretty crazy.
I was eating that.
Okay, now let's try this OBS. Okay, I'm sure that's what the problem is. So we use this, we use this. We start, yes, camera, and started. Now it should be broadcasting, and I connect to here. Now, finally. Okay, good. So remind me next time to install the driver before. Oh, where's the driver? Save? Is this save?
Yeah, see.
And then open folder.
Yeah, open folder. Yeah,
This one?
this one.
Okay, good. Then I'll save this here, and then I'll remember hopefully to run it next time. Okay, good. And this one is a recording already?
Yeah, it's already on the road.
Okay, and then I can record here too. Okay, good. So finally we can start. Sorry for the delay. Technical problems setting up OBS Studio and Discord. Something changed on this computer from last week because last week this all worked correctly. And where's my Google Chrome here? So today, last time we already started talking about a small introduction to probability and some of the things that we can do. Um, these are the axioms of probability theory. In fact, those one, two, three, four rules are enough to derive all other theorems about probability. And you can visualize some of the probability questions or problems using Venn diagrams where you have different sets, A and B, and then various versions of what's the set of the intersection here. Well, that would be A and B. And what would be A or B? If I think about this diagram, what's A or B?
Is uh, the total of the A and B minus the A and B.
That's if I calculate it. But right now, if I just look at it visually, then A or B would be everything that's not white, right? Either the orange or the green. That shape. Yeah. Now, if I want to calculate the area of this shape, right? Then I have to take the area of A plus the area of B minus, and because now when you think about it, this area here is A and B, but I've now counted it twice, so I have to subtract it one time. So that means that A or B would be A plus B minus A and B, the intersection of A and B. And then we talked about discrete random variables and the fact that we can have a countable set of outcomes and probabilities of those occurring. If I have an infinite number of values, then what would that be? Well, in that case, it wouldn't be a discrete random variable. Discrete means that there is a finite set of outcomes. Right? If I have an infinite set of outcomes, then it would be a continuous random variable. Like the position of a robot in the world, that would be considered a continuous random variable. And examples of a discrete random variable would be tossing a coin, because there you can only have 3 heads and 2 tails. You cannot have 3.5 heads with the coin. And then we looked at some of the things we can do. So simulating an unfair dice, and how to do that. Here's the Python program to just roll a dice, a standard dice. And what we're checking here is basically the distribution of the random number generator in Python. So if it's a uniform random variable, a uniform distribution, then each value should show up exactly 1/6 time, and you can see they're all pretty much the same here. And then one of the interesting things that you can do is, so you can say, well, can I simulate a unfair random dice? And how would I do that? And we can. I can specify any kind of dice I want. But I have to change the way that I roll the dice, which is this function here. Now, this comes in later on. It's called a weighted selection or roulette wheel selection. And the idea is that visually, what we're trying to do, oh, So let's take this to be 0.2, this 0.7, and this 0.1. And these are the outcomes that I want for my random variable. So I want to roll a 1, roll 2, roll 3. And I guess I could, since we're talking about that, let's 0.4, 0.15, 0.25. So this will be roll 1, 2, 3, 4. Five, and 6. Now, since this is a discrete random variable, I need to now patch up the numbers so that they add up to 1. So I have 0.675, 595, 0.1, 0.2, 0.1525, 3, so 0.345, 6570, 70, 90, and over 6, 10%. So now they should add up to 1. And now I want to draw a random variable with exactly these weights. So what we mean is that if I draw if I roll the dice many times, then I want 1 to appear approximately 0.1 times or 10% of the time. And to approximately 20% of the times 3, 4, 5, 6. Right? So that's what I mean by uh, rolling the dice of an unfair dice. So now, how do we do that?
Just using uniform random number generator.
Okay, but if I use a uniform random number generator, then I get a number from 0 to 1 with a uniform distribution.
Yeah, and you can simply multiply by six.
Okay, then I get a fair dice,
Yes, a fair time.
which means I would get 1 with 0.1, 165, 1 over 6, 185 probability. But I want 1 to appear with 10% probability, not with 80% probability.
Oh, oh. So you can just using your fair time, yeah, and look up the table you just created and to check if you uh, if you select to 0.4, you will go to 3. Right?
If I throw 0.4, I will go to 3. So yes, that's correct. That's what I would do. Um, but in general, how would that work? I mean, I don't want it just for this one fair dice, right? But what I can do is the uniform distribution will give me a value from 0 to 1. And but what I want to return is something that's proportional to basically the size of these areas, right? The weights that I assign. So huh, weird connected things. Okay. I know I can generate a random variable with probability 0 to 1. And then what I want to do is this roll 5 should be hit 20% of the time. So one way of doing that is to take the cumulative values and then simply check, align them like this, and check if I can get, in which box it would have fallen, basically, right? Which part of the range it would fall. So in order to do that, I need to calculate the cumulative sum. That's the easiest way of doing it, and a very common way to do it. So we start with 0, and then here we have 0.1, and then here we have 0.3, and here we have 0.45, and here we have 0.70, 0.9, and the whole thing has to add up to 1. The cumulative sum is to 1. And then bring this down here. And then I can simply start, right? And then go through. So if I roll 0.72, I think I can delete this one. And then have one mistake. Now I have right? So this is what we have. This is then the implementation of this idea in Python. So we create an array with the different probabilities. First, normalize the array to make sure that it adds up to 1, and then calculate the cumulative sum as we go through the array. The only tricky part is you need to sort of worry about the end of the array, because it's easy to see that if my current value, 0.72, is greater than the value of the current box, right? Then that's the roll that I want to make. But if if the next one is larger, then I want to do that roll, right? Because this is going to be larger for each one of those. If the next box limit is greater, then I want to make the roll. So I just have to make sure that if I'm in the last box, I do that roll. I simulate that roll. And here you can see then the outcome. So you can generate any kind of dice, and it will give you the correct distribution. So that becomes important when we are dealing with the particle filter algorithm. And here I basically just run it for multiple rounds to sort of see the distribution of the probabilities that I get. And you can see that we get the distribution for the different dice rolls based on the number of rounds that we have. Now, another important theory in probability is the central limit theory. It's one of the most important ones. It says that the sum of any number of statistically independent random variables will be distributed according to Gaussian normal distribution of the random variable. So the Gaussian distribution occurs all the time because of the central limit theory, which basically says that if we have a number of random variables and the selection is statistically independent from each other, each drawing is independent of the previous drawing, then we end up with a normal distributed random variable. So what does that mean? If I roll dice 10 times, right, and I add up the values of the dice that are rolled, the number of points that are rolled, if I add those up, then what will be the value of that particular random variable?
You are multiplied by 6.
21. Why 21?
So if you adding 1 to the 6, it's not 1.
Why would I add 1?
Because you want to get the average of the sum of the 5 points to do the central.
Correct, yes. So if I take 10 dice rolls, right? I take one dice, I roll it 10 times. Then I add the numbers up. Then what will happen? What will the distribution look like? Which values am I going to get? If I take 10 dice, right, and I add up their sum, then clearly the minimum number I can get is 10, right? because I roll at least one. So I can never have a 6 or a 3 or anything like that. I also can never get anything larger than 60, correct? That's the maximum I can get. So even if I roll 6, 6, 6, 6 all the time, right? Then I still end up with 60. So anything past here as maximum, anything past here will be 0. This will be 0. So this is the most interesting part. What does that look like?
There will be a mountain line.
A bell curve.
Yeah.
Yes. And the peak will be
In the middle.
so that will be 35. And we will get a bell curve shape here. And that will be the sort of normal distribution shape that we have. The normal distribution is defined. So this will be proportional to a normal distribution, which is defined by two values. And the two values are
Mean and deviation.
the mean, mu, usually, and the standard deviation or variance sigma. So the mean is going to be 35 in this case. Any ideas what the sigma is going to be? That is harder. It actually grows linearly with the number of rows that we have, and it decreases linearly with the number of rows that we have. So we can write a Python program to actually try that out, right? And you should try that yourself now. So before you look at the solution, implement the Python program, which simply takes rolls a fair dice n times for n equals, and actually this effect occurs quite quickly. So it will show up after 6 dice roll. That's actually how the simplest algorithms work for generating a Gaussian distributed random number. They actually just use, because on a computer, there's no instruction to generate a Gaussian random number. In fact, generating randomness on a computer is extremely hard for high security applications. It is very, very difficult actually, because we don't really have a source of randomness in a CPU, or not one that we can actually use at a reasonable speed. If you need to generate a million random numbers, then you cannot have a random number generator that takes a couple of minutes per bit. So on the computer, we can really only generate pseudo-random numbers, which works by sort of taking some math and then generating a uniform distributed random number, 32 bits or 64 bits, and then we still need to generate from that a Gaussian distributed random number, normally distributed random number. That is done in the simplest algorithm. That's done by simply calling the uniform random number over and over again and adding up the values in order to get a Gaussian distributed random number. So try and implement this. Simply take a random number using random.random and then add up the values after, usually it's 6, but we can do 5, 10, 15, 20 times. So the sum of 5 rows, sum of 10 rows, sum of 15 rows, and sum of 20 rows, and then plot the results. So plot the histogram of the results. How often did you get a number between uh, from 0.1 to 0.2? Like just put it into n number of buckets. So for that, you want to use the histogram function of Matplotlib, which is actually quite powerful. You can do that kind of drawing very easily. And remember, it's not the individual values, but the sum of the values that you need to add up in order to make a normal distributed random variable. So you have to open your own Python workbook, yeah. Okay. And then sort of use the programs that I wrote as a template. So you want to import the various libraries, matplotlib.pyplot. If you look at my notebook and look for the import statements, also the ones you want to use.
Is the can is can die throwing at one time?
Pardon?
Is the question is the can we have can die and throwing at the same time?
That doesn't matter whether you throw them at the same time or one after another. If you only have one dice, you can throw it 10 times.
Okay.
What's the important part though?
for the power. The, uh, the distribution of the byte number is the average of the dice throwing at that time, at one time.
You need to sum them up, yes, but also the throw has to be statistically independent. So, for if I pick up a dice, right, and then I throw it correctly, like I throw it, then I think we can all agree that that statistically is independent, right? But if I if I roll the dice, right, and then I pick it up and I just drop it again, then the rolls are not statistically independent anymore. Because uh, if I throw it from here to the door and it bounces down, right, then there'll be lots of turns and twists, and each one of those is random. So the number that I would get if it's a fair dice would be independent of the previous roll. But if I only pick it up like this and then roll it like that, then there's a much higher chance that if I have a 1 up here, I get some other value, right? That is maybe the 6 on the other side. So in that case, the throws would be not statistically independent. If your random variables are not statistically independent, then your um, then this central limit theorem cannot apply or does not apply, or it may not apply. So a lot of work in the statistics and probability is actually about trying to prove the relationship between random variables, estimating their variance, checking whether they're statistically independent. And the reason for that is because if events are statistically not independent, then the math becomes too complicated. Then we cannot really make any prediction. And we'll talk next class about the Bayesian reasoning and Bayesian probability and the Bayesian theorem. That one is sort of a very interesting case because even though in reality we know the random variables that we're combining, they are statistically dependent, right? In practice, we just ignore it. We assume that they're not statistically dependent. And the results that we get, it works in practice, which is the surprising thing, and it works surprisingly well. But statistical independence, in this case, yes, it doesn't matter if you roll 10 dice at once, or if you roll one die 10 times in some of the numbers. That doesn't actually make any difference. As long as it's a good roll. I mean a fair roll, not like flop. Right? If you throw it across the room, then I would say that's probably a fair roll, unless you have extreme skills with your fingers and your motor skills are superb. And here are some of the libraries that you want to include in pretty much any Python program. Most Python programs use those. It goes to the one big batch. Actually, block that graph. So if the central limit theory is correct, right, and you sum up the values and then you plot the distribution, then your chart should look something like this, right? If your output doesn't look like that, then either the central limit theory is wrong, which is rather unlikely, or there's a bug in your program. How many dice did I say? 10, right? And probably a good uh, policy, a good habit to get into is to always label your graphs. Because if you use them in your master thesis, then and you don't have your axis labeled or your graph labeled, then your supervisor is probably going to complain. So here would be our output. Um, so this would be a standard line plot of the sum that we got for the number of rolls. So here I roll the thing 100 times. Now, this chart is accurate but really meaningless, right? Because it just shows the different rolls that we have. So it's not very insightful. So instead, you want to plot the histogram, and you want to plot how often do I get a value around 35? How often do I get a value around 36, 37, so on and so forth. So using matplotlib, it's easy to generate plots. You want to make sure that the visualization actually sort of makes sense or provides some insight. Because this chart right now is completely, not completely, but it's fairly meaningless, right? It doesn't really allow us to say much. You could sort of argue that it does show you what the average is because there's sort of many points around here, and if you go, okay, then I can see the average somewhere there. But that's not, there's no way to actually figure out what the or a good way to figure out whether this follows a normal distribution or not. So it's not very insightful. So you want to do a better chart, a better plot. However, I could make that plot a bit more interesting. Um, and so we add a legend. So I can plot the average line as a dashed line, showing the average of the roles, which is now just around 35. So that's what we would expect. So so here's our sample average or mean formula. So what's the formula for the standard deviation?
Uh, First, you need to take derive the mean and
Yeah.
subtract every sample from the mean.
Mhm.
Yeah. And taking the square of it. Then finally taking the average of this sum.
Correct, yes. So I'm trying to measure how much spread I have in my distribution, right? And that means for a, if I have the whole population, right, then I want to know how far spread out that is. Then what I do is I take the difference between the mean and the actual value. I square that to get a positive number, sum them up, and then calculate the square root of that average. And that makes sense. So we can write down that formula, but there's a couple of sort of caveats that in practical terms are not so important, but for mathematicians and statisticians and probability researchers, they consider them to be important. So we'll go through that. So for standard deviation, there's sort of two versions of it. If you look up the standard deviation, yeah. So remember, what we're trying to calculate is to get a measure of the spread of the distribution, right? Which you would think a good measure of that spread would be the average of the differences between the values and the mean of the distribution. So the variance indicated by sigma square would be it will be the difference between my current sample minus the mean squared, sum that up, and then calculate the average of those by dividing with through n. And the standard deviation then is
the square root of the area.
correct. And if you talk to a machine learning researcher, this is what they would take. This is how they would calculate it. But in if you do this if you do this for the population, for the entire population, that's correct as well. However, if you calculate it for sample, so you don't take all the individuals, but only a certain number of them, then the formula changes. And the reason for that is by taking the square of the values here, we're biasing the, the summation. Because if I have a small value, then if I take the square, it'll be even smaller, right? If it's less than 1. If it's bigger than 1, it'll be larger. It'll increase the distance that I add up. So by taking the square, I don't actually get a sort of from 0 to 1 straight line. Not every value, every error difference from the mean is weighted differently. The further away it is, the more I add, right? So the average that I calculate is not really an unbiased uh, summation, but there's a bias towards smaller values because they're penalized less. Like if I have 0.5, right, and then I square it, I end up with 0.25. So an error of 0.5 would only be counted as an error of 1/2 would only be counted as quarter. But if I have an error of 2, then that's counted as 4. So mathematicians, probability researchers, they actually are very conscientious about this, of course, right? So they want to have an unbiased estimate of the variance. And if you read a statistic textbook, then the formula for variance is actually, anybody taking statistics courses here?
Oh, I think there is another version of the previous calculation. It's I think it's the something and minus the average of the mean.
No.
But the square of
That's if you're dealing with it with. I think what you mean is if you're dealing with it as expected values. So we can talk about the expected values. Then you can reformulate the formula, but that's not really what it is. No, if you're talking to a statistician, then the formula will be 1 over n minus 1. So the only difference really is the 1 over n as opposed to 1 over n minus 1. But this took me a long time to be able to accept, because when you calculate the average of something, right, and you have 10, then you expect to divide by 10, not by 9, right? But the statisticians, in order to make the variance actually more, in order to make it unbiased, to get rid of the effect of the squaring of the values, which sort of emphasizes or gives less penalty to small deviations from the mean, they just use n minus 1. And then, of course, when I took the statistics course, I'm like, well, why n minus 1? Couldn't you just, why not n minus 2, right? That seems to, but then you have to be like really a statistician that is much better in statistics than I am. And then they usually just become hand wavy and they say, okay, well, if n is 100, then it already doesn't matter, right? 1 over 100 or 1 divided by 99, the difference is going to be tiny. So what do you care? But that's the unbiased sample in statistics. For this course, we will just stick with the machine learning definition. So, because this one in our sample sizes are large enough that it doesn't matter whether you pick n minus 1 or n, so we can calculate that. But I always thought that was very surprising when you go and take a statistics course and then they tell you that this average is calculated over n minus 1, not n, then that was not something that I had expected. But okay, so this is the definition of it. Then we can also calculate it, of course. And that's actually part of the NumPy library, but just for fun, we can calculate it ourselves. So I have a sample, and I want to calculate the standard deviation. Now implement the Python code that actually does that. So you want to implement exactly this formula. Okay, and sample is your sample set. So let me see how it's going. Okay. Yeah. Okay. That's what I will use to write it down for standard deviation. And after you've done that, then we can put it in the pot, and then we can do the plot that is around infectious moving on. Okay, then standard, yeah, I'm sure you can do that. But I think this is wrong. Yeah. Um, correct, but in for random, I think the right boundary is included. You make it a 7. Just the hover over it, and hit control space, and it should show you. Oh, the NumPy one, I don't know, but go down and open a new code, and then go help and either random or random. In brackets, like help. One above the mark. Okay, so you correct this mark. Okay. Then just calculate the standard deviation. I know, but I mean, with the program, probably this little star stuff. Yeah. Okay, so actually, let me just call this my, because usually you wouldn't write your own mean and standard deviation function, but just as an exercise, like you can just call average, right? And we'll calculate the average. But um, right, and if this is only possible if the length of the sample is greater than 0, then we can return the return value. So to calculate the standard deviation, I need to calculate the mean first, and let's just use the uncorrected standard deviation. So I divide by the length of the sample rather than the length of the sample minus 1. And I only do this if mu is not none, sorry. And now I can also plot the um, standard deviation. Yeah, I said standard deviation, so this would mean I want to return the square root of this, not the actual, otherwise I'd be returning the variance. And here I can make that a little bit better by returning, since I have to calculate, in order to calculate the standard deviation, I have to calculate the mean anyway, so I might as well just return it here. So that I only need to make one call. In order to get both the average and the standard deviation. And we should probably rename that function then. Oh, okay, I'm not sure what I was plotting there. Uh, so now we have a plot which shows our average and the average minus one standard deviation and the average plus one standard deviation. I like the new formatted strings in Python. I think those are really neat. You just always forget to put the F in front. So for this particular role, we experiment, we have a standard deviation of 5.36. So now let's see about the histogram, because that would give us that the same information only in a much more interesting or in a much more relevant visual way. Happened there. This doesn't look very normal to me, but wanted a number of times. See here the bins. I can put in say 30 bins. So with the 100, it still looks pretty rough estimation of normal distribution. Should look better. So let's run some more. That looks like it should. Yeah, so this is interesting. So NumPy rand in doesn't include the right bound, but the random rand in includes both endpoints. use both. So 100 is still 34. Now let's see. Yeah. So we get a approximation of a Gaussian distribution, of a normal distribution, using that approach by using 10 dice. If I increase the number of dice, then we can get better approximations. So let's have a look at that. Two, 5, 10, 20. Two rows, two columns. As many dice. So that would be the layer, that would be the columns. That would be the sum of the roll. Histogram of the y's, 20. And then H2. So here for several die throws, we can plot the histogram then and see how it develops. So this can take 30, 40. So make it 3 rows. Some count like this. So my titles are a little bit too big now. So now if we run it 10,000 times, then our curves become a lot more like normal distribution. Even with 5 dice, that works out. Okay. Why is this one 2? How can I get the bars there? We have 2 clear dots. So Matplotlib has some very powerful functions in order to do different kind of visualizations. The histogram one is really good. Um, or, it helps a lot in visualizing various things. It's very easy to set up and get a quick plot. What did I want to? Oh yes. So y-s average, y-s st is mean and the deviation y-s, and then I can put that in the label. Y-s average, 2 decimal points, standard deviation, 2 decimal points. And yeah, plot with it. Oh, so this scales it, that's a problem, because here it only goes up to 10, so I cannot have intermediate values here, because it just spreads out the whole curve. the problem. So I should normalize it based on the maximum count that I can have, I guess. That will make it look better. So I want to divide this by the number of guys, the number of dice times 6, then I get a number from 0 to 1 always. So then the x-axis won't be spread out. That looked a little bit weird to have the breaks here, but that's only because I have few values here, just trying to match them to these. So I can divide by size times 6. List. Oh, list. Yeah, so that's where it's advantageous to convert things into NumPy arrays, because then you can divide every entry with a scalar. And okay, so we'll leave it like that. So now we have 0.58. Uh, for our, and you can see the standard deviation, how much changes, it then compresses as you add more and more counts to it. So that's a little investigation into the central limit theorem. We can then extend the notion of discrete random variables to continuous random variables, where continuous random variables are now the ones that have a value in an infinite range, um, so from minus infinity to plus infinity. Now, then we can define a probability, um, the, the probability density function, which specifies that the probability that x has the value x, and it provides the density of that function. Now, it's important to realize that for continuous random variables, So I have a function, probability density function defined, x, um, or p of x, and this may be how far, if I send the robot a command to go forward by 1 meter, then the PDF may be defined as p of x. And it'll say, um, let's say it looks like this. So if I tell the robot to go forward by 1 meter, I may get this kind of curve. Right, for the probability density function, which means that uh, after 30 centimeters, there's sort of an increasing likelihood that will keep going, right? But it'll never go further than 1.2 meters, right? Now this depends on my robot, how the control is implemented. Um, let's say this is our probability density function, and then what? How do we calculate the probability that my robot will go forward by exactly 1 meter? Okay, let's just leave it like that. So then a lot of people think that the probability density function x equals 1.2 is the result, right? Is what I want to calculate. Or let me just do a little plot so it maybe becomes apparent. So I just need to have a function that I can integrate to one. So uh, 0, 0.5, 1, 0.7, so up to 0.9, and then I need to figure out what that is. 1.2, let's say. Okay. So if I plot this, then 0, 0.5, so I want to plot it from 0 to 2, 50 samples. Ys is equal to my PDF, x for x in x's. So let's go. If x is less than 0.5, return is equal to 0. Else, if x is less than 0.7, then the return is equal to 0.0 plus 0.x minus 0.5. So this will go up to 0.2. And then from here it will go up to 0.4, 0.6. 0.9, return is equal to 0 plus 7. 2 times This would be 0.2. And this would be 0.6 minus 0.6 minus x minus 0.9 else if x less than, so 0.6, 1.5, So let's see if I made a mistake. Specifying the PDF. 50 and 1,000. Label. Okay, that's not 1.1. Yeah, that's here. It's 1.1. Then 1.1 to 1.5, 0.6, 0.6. So that should be 1.1 plus 0.6, 1.7. 7. So here's our PDF. Now, how can I find out what's the probability that the robot will run 1.1?
The power zero, but not zero. You need a probability exactly is 1 to 5.
Yeah. Then it's actually the probability that it's exactly 1 is in fact, so I would have to, I don't want to stop now, I would have to normalize this to 1, but you're correct. This only gives us the probability density. So if you look at 1.0, for example, and you read 0.6, what does that mean? That means that the density of the distribution at that point is 0.6. It does not mean that the probability of getting 1 is actually 0.6. In fact, the probability of any point is like we already mentioned, it's exactly 0. If you ask the probability of having the robot drive exactly 1 meter, then that probability is going to be 0. Because what we actually need to do is, in order to, so ignore the sum. If I sum this up, I probably won't end up being exactly at 1.0, but we ignore this effect for now. It'll just squash the whole curve up and down. So this is not the result. This is not the value of the PDF at x is equal to 1.2. In fact, the probability of exactly of any single point is 0 always. And that's because in this case you are asking that the robot drives 1 meter, but what you're actually saying is that the robot drives 1.000000000000000 at infinitum meters, right? So what you're basically asking for is a tinier and tinier slice of this whole range. Here. So if I ask what's the probability that the robot drives from 0 to 2 meters, then that should be 1. Right? Because everything there is 0, everything there is 0. So this has to add up to 1. The integral of the PDF has to, from minus infinity to infinity, that integral has to be 1. So the probability that we drive, let's say, 1 meter, and or the probability that we drive from 75 to 1.25 meters would be this integral here. Right? And then I can make it smaller, then the probability is going to decrease. Right? So the probability that I drive from 95 centimeters to 105 is going to be less than from 75 to 1.25. Why? Because 95 to 105 is a subset of 75 to 1.25. So there's no way that the 95 to 105 can can be larger than the probability of running from 75 centimeters to 1.25 meters. And that's just impossible, because probabilities are all positive. There's no such thing as a negative probability. But as I keep decreasing the size of that interval, the probability has to decrease. Right? As I make it smaller and smaller. But if I ask for a single point, then I'm not asking for the probability that the robot drives from 99 to 101 centimeters. If I ask what's the probability of driving 1.00 to 1.01 meters, then that will have some probability. But if I ask for 1.00000000, exactly that single point, there's zero probability that the robot can actually drive exactly that 1 meter that you want. So how do we calculate the probability then? Yes, we have to integrate the PDF over the range that we're interested in order to calculate the probability. So what I get is so the probability will only be defined and non-zero for a range. So, and what we usually mean would be drives 1 meter plus or minus 2 centimeters, for example. Right? Now I have a range from what's the probability that the robot drives between 98 centimeters and 1.02 meters. And now I have a range, not a single point, then that probability I can calculate. And that's how we can calculate probabilities for continuous random variables. Now, colloquially, we could ask what's the probability that the robot is driving exactly 1 meter, that the robot drives forward by 1 meter. But implied in that is that we have 1 meter plus or minus some kind of range that we would still accept, right? So for 1 meter, then it will be plus or minus 0.5 centimeters, for example. But to be precise, we must have a range, not just a single value, if you want to be able to calculate a probability. And that probability then is not given by the values in the PDF. It depends on the integration. So that's our introduction to probability and statistics and continuous random variables. We'll be using those when we're dealing with particle filters, Kalman filters. Next week we will investigate conditional probabilities, the Bayesian theorem, and Bayesian reasoning, and then the week after that we'll talk about Kalman filters, which will be the first kind of slam algorithm that we actually get through. However, the probabilities, I can only caution you, it's very easy to make a mistake when it comes to probabilities. I'll tell you some of the mistakes that we made with our robots when we were dealing with probabilities. But there's some very subtle effects. So you want to be careful and not do things like calculate the probability of an event by just using the PDF value. That's why it's called the probability density function. Otherwise, we call it the probability function. Okay, good. So let me put that graph in there. So what do I actually have? If I can install.
So the recording.
Yeah,
Stop.
please, yeah, you can stop.
Okay.
So that first part is from 0.5